Now, with our calculations, you're going to notice these are going to start to get repetitive. We've got BCAs, we've got ice. You really got to think about what is going on in a solution. And this is also going to apply to titrations, guys. So we can actually calculate what the pH should be at a certain point in a titration, or we can use a titration to calculate a concentration or identify an acid. There are so many uses for titrations, which is why the 162 class is really all about titrations, okay? So I am going to talk about titrations really quick. A titration curve is essentially just monitoring the pH as we titrate an acid with a base or combine them to a certain point, right? So this is really just monitor the pH. Usually one thing is known and one thing is unknown. It's generally the known strong base, right? We use sodium hydroxide like all the time, with an unknown, generally a weak acid or an acid concentration that we don't know or type of acid that we don't know. Okay, so this is what our titration curves are going to look like. We are actually going to take the pH as you do the titration. So instead of using phenolphthalein, because not everything is going to change color at the equivalence point exactly with phenolphthalein, we're just going to take the pH as we go. Okay, it's a lot more accurate actually than that one drop going past the equivalence point. So this is what our curves are going to look like. You're going to get this as the result when you do a titration. So let's see, this is a strong acid, strong base titration here. You'll notice the equivalence point is at exactly 7. Because of the equivalence point, you have the exact same amount of strong acid and strong base. So if they neutralize each other completely, it's going to be at 7. Okay, that's the equivalence point. So the equivalence point in our titration curve, you'll hear me use the term inflection point. It's the inflection point in that graph. That's where it is. And you'll notice before that, it stays super acidic. And then after that, it gets super basic, because any amount of strong acid or strong base is really going to affect that pH. Okay, so it stays really acidic, hit that equivalence point, it gets really basic. Okay, so this is essentially a very drastic inflection point. Indicates that this was a strong acid, strong base. Also, that I start very low. Well, this one is actually starting at 1, and that this is very flat. Okay, this is what your titration curve for strong acid, strong base are. So I am going to go through the calculations for finding the pHs of strong acid, strong base titrations, and we can actually calculate what the pH is going to be at every point along this curve, if we know how much stuff is at it. So I'm going to show you how to do the calculations before you hit the equivalence point, the calculation at the equivalence point, and the calculations beyond the equivalence. Excuse me. So what we're going to do, I'm just going to show you one of each. So I'm looking at this. I've got what is the pH of a titration using 0.1 molar sodium hydroxide solution on 25 milliliters of 0.1 molar hydrochloric acid when the following amounts of sodium hydroxide have been added. So it looks like I'm starting, this is what's in my little flask, right? Okay, this is what I'm adding. This is in my burette. And I'm adding little bits at a time. Okay, so I'm adding 5 milliliters, 10, so on and so forth, all the way to 35 milliliters. Now, I'm trying to make the numbers easy so we can kind of think about this. I've got a 0.1 molar hydrochloric acid solution, and I have 25 milliliters of it. So if I am titrating it with the exact same concentration of sodium hydroxide, how many milliliters should I need to reach the equivalence point when all of the acid has been neutralized by all of the base? 25 milliliters, right? So this should be my equivalence point. Since this is strong acid, strong base, the pH here should be 7. All right, so everything before that should be very acidic, or after that should be very basic. All right, so what we're going to do is, you guessed it, a BCA, but we're not going to need to do ice because none of these are weak. They are strong and strong. Okay, so calculations before the equivalence point for a strong acid, strong base titration. Essentially, first thing you need to do is BCA. Okay, we have to figure out how much acid is left in there to calculate the pH. Yes, there's excess acid because we haven't gotten the equivalence point yet, but how much? So you have to do a BCA. And then we can find the pH from the H plus leftover molarity. Okay, so essentially what's going on in this solution, I'm going to draw like a flask for each one of these, okay, is I have a bunch of H pluses, that's what's affecting my pH. So that's what I need to look at. Okay, I've only neutralized, maybe I've neutralized a little bit of it. So I have maybe like a water in there, but I do not have any extra OH minus. All right, so BCA, I'm going to do for 5 milliliters. So below, I'm going to show you the calculations for 5 milliliters. Okay, so I've got strong acid, strong base, makes water whenever they're neutralized. It's always going to be H plus and OH minus when you're doing strong acid and strong base. Okay, I'm going to do a B and a C and an A. So beforehand, how many milliliters how many moles, right? BCAs and moles do I have? So 0.025 times 0.10 means I'm starting with 0.0025 moles of acid. So 0.0025 moles of acid. How many moles of base? Well, 5 milliliters. Okay, I'm doing for 5 milliliters. So 0.005 times 0.10 means I added 0.0005 of this. Nobody cares about the water. All right, so they're going to neutralize each other. Minus x, 0.0025 minus x, 0.0005 minus x. Obviously, I have less of this, so I will have no hydroxide excess in there. I'm just going to have some H plus still. So it's really going to be 0.0025 minus x in this case is 0.0005. That goes right there. And so I have 0.0020 moles of H plus. Now that makes it really easy. This was step 1. That makes it really easy for me now to calculate my pH. If I have 0.0020 moles of H plus okay, what is my volume of solution? Well, I added 5 milliliters and I started with 25, so I have 30, right? So I had 0.025 plus 0.005. That's my liters. It's going to give me not a number that I wrote down. There we go. 0.002 divided by 0.025 plus 0.05. I get 0.06667. So the pH is the negative log of that. 0.06667 is 1.18. Okay, so I found the pH after I had added 5 milliliters. So this one is 1.18. Now I can do it after I add 5 more and 10 more and so on and so forth. And you'll notice as you calculate these, all calculated the same way, you get 1.37, 1.95, 2.28. So it's gradually going up, 3.39, 3.40 until I hit that equivalence point, 7. Now I know it's 7 at the equivalence point because all of the acid and base have neutralized each other. Because if you write it out, right, this was my equation. If I have the same amount of both, all of it has turned into water. So my pH here is 7. Now, after the equivalence point, I should have excess hydroxide. So I'm going to draw, this was my equivalence point, right? I don't have any excess anything. It's all water molecules, all of it. But after the equivalence point, after I've neutralized all of my acid, now I'm going to have waters in there, yeah. But now I'm going to have a little excess OH minus because I would have added past the equivalence point. So this is going to work the same way. You're going to do a BCA to figure out how much hydroxide is left. And then you'll use that excess hydroxide, excess OH minus, to find, right, your POH and then the pH. Okay, so it works very similar to what we did at the first part. Okay, I'm using the same equation. I got the same thing going on. H plus OH minus makes water. B, C, A. Let's do at 25.2 milliliters. So this is at 25.2 milliliters. That's the calculation that I'm going to do. So that means my acid is always the same, right? I never added in any more acid. I'm just constantly adding more base. So I started with 0.0025 moles of acid. But now after 25.2 milliliters, that is 0.00252 moles of base. Minus X, minus X, minus X, minus X. Now this time, my hydrogen is going to equal 0, my hydrogen ion, because I've completely neutralized it all. It's also a smaller number, so X is 0.0025. Plug that in, I have 0.00002 moles of OH minus left over. Okay, now this is what's in excess. So I'm going to do my POH because I have hydroxide. So that's 0.00002 moles of OH minus over, what are my total liters? Well, I had 0.025. That was how much acid I started with. I've now added 25.2 milliliters. So that's 0.0252 liters. So whatever that is. And I get that the POH is 3.40. So my pH is 10.60. So even after you go 0.2 milliliters past the equivalence point, your pH jumps to 10.60. Okay, so I'm going to put that up here in my table. It went to 10.60. Now you can calculate all of these and you'll notice it'll just keep becoming more basic. 11.68, 11.96. They are all calculated the same way. Okay, the only number that is going to change for these, if you look down here, the only number that's going to change is this hydroxide, how much hydroxide you added, and that volume. Okay, so that's the only thing that's going to change for each of those. I got extra hydroxide, so it makes it more basic each time. All right, so I recommend doing those on your worksheet, and yes, you do have to calculate them all, but you only have to show me one calculation. All right, good luck, and ask me questions if you have them.